Okay, look at these. Rational functions, trig waves, piecewise things with corners, the kind of curve that shows up in an exam and your stomach drops. Here's what nobody tells you. Almost every graph you'll ever be asked to sketch is one of 5 shapes, stretched or flipped or shifted around. 5. That's the whole list. So let's meet them. First up, f of x equals x, a straight line. Then x squared, the u. Then x cubed, the s. Then x to the 2n, a steeper u. And x to the 2n minus 1, a steeper s. Everything else? Those same 5, stretched, flipped, or slid. But before we get into them, we should talk about why most people never learn it this way. There are dozens of graphs I have to memorize. And it looks that way, right? Every new topic piles on more curves, none of it carries over, so you memorize pictures. Here's the cost: plainly, a remembered picture only answers a question you've already seen. Meet something unfamiliar in the exam, and you've got nothing. Because the pile never stops growing, and nothing you learn about one curve helps you with the next. They're disconnected. Then exam day comes, an unfamiliar function shows up, and you've got nothing to fall back on because you learned pictures, not rules. A remembered picture only answers the exact question you've already seen. So what's the alternative? 5 shapes, and one test that tells you which family any power belongs to. That's it. A rule answers questions you've never seen before. An unfamiliar curve stops being unfamiliar, because you can work out its shape instead of straining to recall it. Work it out, don't remember it. And it collapses even further than 5. Here's where we're headed. Those 5 shapes fold down into 2 families, even and odd. And the whole ordering story hinges on one point, plus or minus 1. 5 shapes become 2 rules in one crossover. Everything from here is filling in that picture, starting with why powers of x behave so predictably. A polynomial looks like a mouthful, a naught plus a 1x plus a 2x squared, all the way up to a n x to the n. But strip off the coefficients and what's left is a row of single powers of x. That's all a polynomial is. And each of those powers, on its own, does one of exactly 2 things. 2. That's the whole menu. Either the curve looks identical on both sides of the y-axis, the left half is a mirror of the right, and we call that even. Or it looks like itself rotated 180 degrees about the origin, and we call that odd. Mirror, or spin. So how do you tell which one you've got? You can do this in your head in 5 seconds. Take f of x equals x to the n, and swap in negative x for x. If nothing changes, if f of negative x equals f of x, it's even, mirrored across the y-axis. If every sign flips, f of negative x equals minus f of x, it's odd, 180-degree spin. That check pays off immediately. Here's the payoff. Plot the right half of an even function, and the left half comes free. Swapping x for negative x changes nothing, so it folds straight across the y-axis. You've drawn half a graph and gotten a whole one. Odd powers do the same trick, spun through the origin instead. F of x equals x. It's called the identity function because the output is always exactly the input. Feed it -3, you get -3. Feed it 2, you get 2. Plot those pairs and they line up perfectly, a straight line through the origin, tilted at exactly 45 degrees. Boring? Maybe. But it's got properties worth pinning down. You can plug in any real number and get a real number back, so domain and range are both all of our parity? Odd, swap in negative x and you get negative x, sign flipped. Which means its symmetry is about the origin, spin it half a turn and it lands right back on itself. And this line has a second job. Keep a sharp mental picture of this exact line, because later on you'll reflect other curves across it to find their inverses. The 45-degree line is the mirror axis for the whole inverse function story. Plant that seed now. Write the power on x was 1. Crank it to 2 and everything changes. A straight line is the whole story when the power on x is 1. Raise it to 2, and the line folds. Watch, the left arm swings up, the whole thing bends at the origin, and you get a bowl. That's the parabola. Let's build it properly. Build it from a table. -3 gives 9. -2 gives 4. -1 gives 1. 0 gives 0. Then 1, 4, 9 on the way back up. Notice how the outputs come in matching pairs on either side of 0. Drop those 7 points on the grid, join them, and there's your u. That pairing isn't a coincidence. Run the test. F of negative x is negative x, all squared, which is x squared, which is f of x. Nothing changed. Squaring a negative gives you exactly the same answer as squaring its positive twin, so the left half is a perfect mirror of the right. That's what even means, and it has one more consequence. A square can never come out negative. Ever. So the curve can't dip below the x-axis, that whole region is off limits. The lowest value it reaches is 0, right at the origin, which makes that the vertex. Range, 0 to infinity. And here's the thing about this shape, it's not one curve. Every quadratic you'll ever meet, y equals ax squared plus bx plus c, is this exact shape. Change a and it gets narrower, or wider, or flips upside down. Change b and c and it slides around the plane. But it's always the same u, same family, different costume. Now add one more factor of x. Squaring folded every negative input up to match its positive twin. Now multiply by x one more time and watch that fold vanish. Nothing gets discarded here. Every sign survives, so the left arm drops back down below the axis into an s. F of x equals x cubed. Negative 2 goes to negative 8. Negative 1 to negative 1. 0 stays 0. 1 to 1, 2 to 8. Join them and you get that s climbing steadily from bottom left to top right, no dips, no humps. Domain, all of our range, all of our plug in anything, get anything back. And the parity test? Cubing a negative keeps it negative, the sign flips through cleanly. F of negative x equals minus x cubed, which is minus f of x. Every sign flipped, so it's odd. Which visually means, turn the whole graph 180 degrees around the origin, and it lands exactly back on itself. Opposite quadrants. There's another feature worth noticing. Follow the curve with your finger from bottom left to top right. It never turns around. Not once. It rises the entire way, across every single real number. A curve that only ever moves one direction like that has a name, it's monotonic, and this one's monotonically increasing on all of R. But there's a spot that trips people up. Zoom in on the origin. The curve does flatten out for an instant right there, tangent perfectly horizontal, slope 0, and that looks exactly like a turning point. It isn't. Compare it with a parabola's vertex, where the curve does reverse. Here, the cube pauses and keeps on climbing. No peak, no dip. Now notice something x and x cubed did the same thing. X and x cubed both passed the odd test. Both spin onto themselves through the origin. They're not two separate facts, they're two members of one family. And x squared is sitting over there on its own, waiting for company. So let's widen the lens on the even side first. X squared was never a one-off. Every even power x to the fourth, x to the sixth, and on forever draws the same basic u. Just tighter or looser. Domain still all of R, range is still 0 to infinity, and every one of them passes the even test, for every n. What's interesting is where they meet. Plug 0 into any of them, you get 0. Plug in 1, you get 1. Plug in negative 1, and because the power's even, you get 1 again. So x squared, x to the fourth and x to the sixth all cross at exactly the same 3 points, the origin, and plus and minus 1, 1. Between those crossings, they separate. Take a fraction, say 0.5. Square it, you get 0.25. Square that, 0.0625. It's shrinking, fast. So inside the band between negative 1 and 1, the higher the power, the harder the curve hugs the x-axis. X squared sits highest, then x to the fourth, then x to the sixth down at the bottom. Now step outside that band. Now step outside the band. Past 1, multiplying makes things bigger, not smaller, so the rule flips. Take x equals 2. Squared, that's 4. To the fourth, 16. To the sixth, 64. The higher power runs away fastest, and the ordering is the one you'd expect. X squared is less than x to the fourth, less than x to the sixth. This, fractions shrink when you raise them to a higher power, and numbers past 1 grow. That's it. That single sentence lets you rank any two of these curves without drawing either one, without a calculator, without a table. But there's a reason it's this clean for even powers specifically. Squaring erases the sign. The minus sign vanishes. Which means the even family only ever had to care about the size of x, never which side of 0 it started on. Swap in an odd exponent and that shortcut disappears, the sign survives the power. Which is going to make the odd family a bit more interesting. Same deal on the odd side. X, x cubed, x to the fifth, and onward all the same S shape, all threaded through the origin, with x to the fifth flattest between -1 and 1 and steepest outside. Domain, all of R, range, all of R. And every single one of them is odd, for every n. Where do they cross? Same three crossing points, but look closely. 0, 0, 1, 1, and -1, -1. That last one's the difference. The even family met at -1, +1. The odd family meets at -1, -1. Mirrored through the origin, not across the y-axis. Start with the positive side. For positive x, nothing new. Between 0 and 1, the shrinking rule kicks in, higher powers get smaller, so x is above x cubed is above x to the fifth. Past 1, they grow instead, and it flips x below x cubed below x to the fifth. Identical to the even family. Cross to the negative side, though, and things get sneaky. Take -0.5. Cube it, -0.125. Fifth power, -0.03125. The sizes are shrinking, same as before, but on the negative side, closer to 0 means larger. So the ordering flips. Here it's x less than x cubed less than x to the fifth. Exactly backwards from the positive side. And it flips again below -1. Below -1, take -2. Cubed, that's -8. To the fifth, -32. They're marching downward, further and further below 0, so the bigger the power, the smaller the value. Order flips back x greater than x cubed greater than x to the fifth. Count them up and something becomes obvious. The even family needed two bands, split at -1 and 1. The odd family needs 4, below -1, -1 to 0, 0 to 1, and above 1. Twice the segments, because the sign matters as well as the size. The magnitudes behave identically, it's the inequality signs that turn around wherever x is negative. Which is exactly where people lose marks. Here's where people lose marks. You work out that x beats x cubed beats x to the fifth between 0 and 1, then paste that ordering straight onto the negative side. Wrong. At -0.5 you get -0.5, -0.125, -0.03125, closer to 0 means bigger. Every inequality flips. Here's the question that shows up constantly. Given some x, put x squared, x to the fourth and x to the sixth in order. No calculator. No table of values. No sketch. You don't need any of it, because one question settles the whole thing: which side of plus or minus 1 is x on? That's it. Let's answer it twice. Say x is not 0.5. X squared is not 0.25. X to the fourth is not 0.0625. X to the sixth is not 0.015625. Each one's dramatically smaller than the last, so the order reverses: x squared beats x to the fourth beats x to the sixth. Now push x past 1. Now x equals 2. 4, then 16, then 64. Multiplying by something bigger than 1 grows things, so higher powers grow faster and the order is the one your gut expected all along: x squared under x to the fourth under x to the sixth. Two cases, two opposite answers, and the switch happens at one precise place. Right at the boundary, everything ties. At x equals 1, every power equals 1. At x equals -1, every even power equals 1 too. That's why all these curves squeeze through the same corner points, and why the ordering flips there and nowhere else. Plus or minus 1 is the hinge. Everywhere else in the whole real line, the ordering is locked. Which someone did bother to check. 200,000 random values, on each side of the hinge. Every single one obeys the rule. Not one exception. It's not a rule of thumb or an approximation you should be nervous about, it holds. Though there is one thing to watch out for. Everything we just ranked was even powers, where only the size of x matters: 2 bands, done. Swap in odd powers and the sizes still behave the same way, but the inequality flips wherever x is negative. For bands, not 2. Take the even rule and drop it straight onto odd powers and your answer comes out exactly backwards. So remember where we started? You were told there were dozens of graphs to memorize. There weren't. There were 5 shapes, 2 families, and 1 crossover point. And that's enough to rank curves you've never drawn, at values nobody gave you, in an exam question you've never seen. That's the difference between a picture and a rule. Here's all of it in one table. So here's everything, in one table. Screenshot this one. 5 functions, and look how they collapse into 2 patterns. The odd ones, x and x cubed and x to the 2n-1, all range over the rails, symmetric about the origin, always increasing. The even ones bottom out at 0 and fold across the y-axis. 2 families. That's the whole picture. The ordering rule, condensed. For even powers, only the size of x matters. Inside the band, a higher power is smaller; outside it, a higher power is larger. Everything ties at plus and minus 1. For odd powers, check the sign too, same sizes, but the inequality turns around on the negative side. For bands, not 2. That's the whole video, really. So, 5 shapes, not dozens. 2 families, even and odd. 1 hinge, at plus and minus 1. Get those and unfamiliar curves stop being unfamiliar. Next time we're doing something sneakier: 2 modulus signs, 2 completely different graphs, and the difference is smaller than you'd think. If this is your kind of thing, stick around, there's plenty more coming.